Welcome. Today we shall discuss electromagnetic radiation from accelerated charges. For the present at least, most of the information we receive from celestial bodies is from the electromagnetic radiation they emit at various wavelengths. To understand objects like pulsars, supernova remnants, quasars, active galactic nuclei, etc., we must have some understanding of several radiative processes which are important in astronomy. Some of the processes we need to understand, at least briefly, are thermal Bremsstrahlung, cyclotron radiation, synchrotron radiation, content scattering, and so on. And for each of these mechanisms, we need to understand the actual radiation mechanism, the spectrum or the frequency content of the radiation, if there is any characteristic frequency in that mechanism, the angular distribution of the radiation, polarization, etc. Let's begin. The electromagnetic field is specified by the electric field and the magnetic field. Both are functions of position as well as time. Alternatively, you can use a scalar potential, usually denoted by phi, and a vector potential, usually denoted by A. Both phi and A are once again functions of the position as well as time. And the relation between these potentials and the fields, E and H, are given in these two formulae. The electric field is minus gradient of the scalar potential minus 1 over C dA dt. And the magnetic field is the curl of the vector potential. Now, you may or may not be familiar with electrodynamics using the scalar and vector potential. So, I suggest a couple of references. First of all, please consult Feynman Lectures in Physics, the 3 volumes. This is an excellent reference for any topic in physics. I still use it almost on a daily basis. For this particular subject, namely electrodynamics, perhaps you could consult Electrodynamics by Griffith, which is used very often by undergraduate courses in physics. So let us begin. The first concept we must understand is the concept of a retarded potential. Here is a charge moving along a trajectory which I have indicated by the green line. At that particular point, the charge is there, its velocity vector is in that direction, and its acceleration is in that direction. We are interested in the electric and magnetic fields at a distance capital R from the charge at a time t at a distance small r from the location of the charge. Now, the important thing to appreciate is that Maxwell had asserted that the velocity of light is constant, it's uniform, and it is absolute. Indeed, the very existence of electromagnetic radiation is a consequence of this absoluteness of the velocity of light. Therefore, if we want to calculate the effect at this point, at a time t, when the particle is here, we really must be considering the effect when the particle was at an earlier time, which is known as t retarded, because it will take that much time for the signal to reach from there to there. Another way of saying that is, the Earth is at a certain position in its orbit around the Sun. It takes 8 minutes for the gravitational influence of the Sun to reach the Earth. So you have to ask the question, is the force between the Sun and the Earth along the line joining the Sun and where the Earth is right now, or where the Earth was in its orbit 8 minutes ago. So you think about it. Anyway, that's the concept of retarded time. So you must, in order to calculate the scalar potential or the vector potential and therefore the electric and magnetic fields at a time t, you must really consider the location of the charge at an earlier time. Now, let us consider a collection of charges in a certain volume. And let us say we are interested at that point over there, which is at a distance r subscript 0 from the center of the charges, and a particular charge is at a distance small r from the center, and the distance between the charge at that time and the point of interest is capital R. So here you have a little triangle, and let us now consider the retarded potential due to this collection of charges which are in motion. The scalar potential at a time t is given by the formula 1 over capital R integral of the charge density rho integrated over the volume. If there was only a single charge and if the charge was not moving, then it's simply E over R. That is the scalar potential, and you know that is the Coulomb potential. Now please notice that if I'm interested in the scalar potential at a time t, I must consider the charge distribution at an earlier time, t minus R by C. R by C is a time. It is a time that will take for electromagnetic radiation to reach from there to there. So that is the concept of the retarded potential. Similarly, the vector potential is 1 over C times R integral of the current integrated over the volume. If you are just dealing with a single charge, then the current is E, the charge, multiplied by V, the velocity. But if you have a distribution of charges, then you have to integrate the current density over the volume, just as you have to integrate the charge density over the volume. Again, the vector potential at R and T is related to the current density at an earlier retarded time, T minus R by C. This is the essential difference between what we did before Maxwell and what we have to do after Maxwell. Now we can do a simplification. Capital R can be, if you look at this triangle, vector capital R is equal to modulus of vector R naught minus the vector R. Now you can expand this and write an approximate relation that this modulus of this vector R is R naught minus the dot product of R with the unit vector n along this direction. R dot n is that projection, R cos theta. So if I subtract from R naught R cos theta, small r cos theta, then I get capital R. So let us now write the retarded potentials. The retarded scalar potential is given by integral of rho t minus capital R by C, which I have written as rho t minus with this simplification over there. And similarly, the vector potential, which can be written there. And all I have done is, instead of R over C, I have replaced it by R naught minus R small r dot n divided by C. That's all. I've not done anything. And it's a very good approximation if the size of the system is small compared to the distance at which you're calculating the scalar and vector potential or the electric and magnetic fields. Now, at large distances compared to the size of the system, as well as the wavelength, the field over small distances can be regarded as a plane wave. In other words, the expanding spherical wave, when the radius of the sphere wavefront becomes very, very large, at very large distances, this can be regarded as a plane wave because you will be detecting only a small portion of this spherical wavefront. Now, if you now look in books like Griffith or Jackson or Landau and Lifshitz, if you are more advanced in your preparation, then you will find expression as follows. The magnetic field is 1 over c times dA by dt cross the unit vector n, which I showed in the previous slide. And the electric vector is 1 over c dA by dt cross n and another cross product. What this is telling you is that the magnetic field is perpendicular to this unit vector n, because this is a cross product, and the electric field is perpendicular to the magnetic field. Therefore, the electric field and the magnetic field are perpendicular to one another, and each of them are perpendicular to the direction of propagation of what we shall now call as the electromagnetic wave. So we are dealing with transverse electric and transverse magnetic fields. Now, there is an important point to notice, namely that the vector potential is proportional to 1 over r. All right, this is an important point to keep in mind. So let us now understand this properly. The important thing to understand is that at very large distances, when the wave can be regarded as a plane wave, this expression and this expression can be taken for the magnetic field and the electric field respectively, then the electric field as well as the magnetic field, which are derivatives of the vector potential, are inversely proportional to the distance r. This is the signature of the radiation field, the transverse radiation field. If you remember, in electrostatics, according to Coulomb's law, the electric field would have been proportional to 1 over r squared. But now we are talking the electric field being proportional to 1 over r, and the magnetic field also being proportional to 1 over r. This is an essential difference between the velocity field and acceleration field, as I shall now explain. Let me once again remind you that the electric field and magnetic field are perpendicular to one another and perpendicular to the direction of propagation. Now let us look at this diagram. This is the x-axis. There is a charge moving with a uniform velocity, and I break the charge and I bring it to a halt at x equal to 0 at time t equal to 0. At that point, at clock starts ticking, t equal to 0, the charge has come to a stop. It has been decelerated from a uniform velocity to 0 velocity. Now, at a time t equal to 1, inside a radius of distance c times 1 second, c times 1 second is a distance. It is the distance up to which the electromagnetic radiation or signal, any signal, would have propagated in 1 second. And that I'm indicating by this semicircle over there. In other words, every point inside that semicircle, the signal, the information that the charge has in fact decelerated and come to a stop at x equal to 0 would have reached every point inside that semicircle, because I have considered a semicircle whose radius is c. That is the distance up to which the signal would have traveled. There you know from Poisson's equation that the divergence of V is proportional to the charge density. The electric field will be radial and will be pointing towards the location of the charge. So that's because every point inside that semicircle of radius c knows that's where the charge is. Now, let us consider at the same time t equal to 1 second, the electric field outside this radius whose radius is c. Well, the important thing to appreciate is that the information that the charge has come to a stop at x equal to 0, at t equal to 0, has not yet reached any point outside the semicircle of radius c. Therefore, as far as all this region outside the semicircle is concerned, the charge is still moving with a uniform velocity, and it would have reached the point x equal to 1 at t equal to 1. Therefore, for all observers outside this semicircle, the electric field will once again be radial according to Poisson's equation. Divergence of V is proportional to rho, and it will be directed towards this point x equal to 1. I hope you understand this. So there is an essential difference between inside that semicircle of radius c and outside the semicircle of radius c. Inside the semicircle, every point has the information that the charge has come to a stop, whereas outside the semicircle, no point outside the semicircle knows that the charge in fact decelerated and came to a stop at x equal to 0. It would assume that the charge in fact moving uniformly and would be at a point x equal to 0. The information about the deceleration has not yet propagated beyond the distance c, where c is the speed of light. Now, the only way these two radial fields can be matched or connected is by having a transverse field. And here is the transverse field. The field is radial inside, the field is radial outside, emanating from this point. The only way these red lines and the blue lines can be matched is by having a transverse electric field along the circumference of this semicircle. The thickness of the transverse electric field will be determined by the duration of the acceleration. Please refer to Feynman lectures for a brilliant discussion of this point. Therefore, we are talking about a transverse electric field, and this transverse electric field will propagate with a velocity c, and this electric field will drop off as 1 over r, not as 1 over r squared. This is the radiation field. So now, let us proceed. Let us now make a simple approximation, which is known as the dipole approximation. What is this approximation? We already said that this vector r can be approximated by r naught minus small r dot n, where n is the unit vector in the direction of the radiation. In this dipole approximation, we are going to assume that the retardation time, which is t minus r by c, t minus r by c. Remember, r is going to be different for different charges, because r is capital R naught minus small r dot n. So this capital R is going to be different for all the charges inside this little volume. We are going to assume that the retardation time is the same approximately for all the charges in this system. Now, when will this assumption be true? There is a constraint on the size of the system, namely, the size of the system must be very small compared to this distance r. Then only you can possibly assume that the retardation time will be the same, approximately the same for all the charges. Also, that the velocities of the charges must be small compared to the speed of light. Because if the velocity of the charges is very large compared to the speed of light, for example, comparable to the speed of light, then you cannot make this assumption. For this to be true, for this assumption to be true, the size of the system must be small compared to the wavelength of the radiation that we are considering, and the velocity of all the charges must be small compared to the speed of light. So there it is once again. Under those circumstances, the vector potential can be written in the following way. The current is simply the electric charge multiplied by the velocity of the particle. So this is electric charge multiplied by V subscript I for the ith particle summed over all the particles. It is this sum which I have written as an integral over there. Summation E times V has been written as an integral of the current density over this volume. Now let us look at it in this way of writing. V is dr by dt. dr subscript I by dt. The velocities of all the particles can be very different. Now, E times r, where r is the displacement of the particle from the center of the system, is the dipole moment of the charge. Therefore, summed over all the charges I going from 1 to n, this summation will give me the total dipole moment of all the charges inside that volume whose characteristic size is L. Therefore, the vector potential is d by dt of the dipole moment. Okay, so this is why this approximation is called as the dipole approximation. This is not rigorously correct, but it is a very good approximation. If the size of the system is very small compared to the wavelength, and if the velocity of the charges is small compared to the speed of light. So, to remind you, the vector potential under this approximation is d by dt of the dipole moment of the charge system we are considering. And since the magnetic field is dA by dt, and the electric field is also dA by dt, the vector potential itself is d by dt of the dipole moment. Therefore, the magnetic field and the electric field will be proportional to the second time derivative of the dipole moment. It will be proportional to d double dot, d squared dipole moment divided by dt squared. So here is the fundamental result. If you are willing to make this approximation that the size of the system is small compared to the wavelength and all velocities are small compared to the speed of light, then the electric field and the magnetic field are given by the second time derivative of the dipole moment. So if the second time derivative of the dipole moment doesn't exist, dipole moment may exist, even the time derivative of the dipole moment may exist, but if the second time derivative doesn't exist, the electric field and the magnetic field don't exist. The transverse electric and the transverse magnetic field don't exist. So to repeat, in the dipole approximation, the radiation is determined by the second time derivative of the dipole moment, d double dot. Charges can radiate only if they have an acceleration, and charges in uniform motion do not radiate. This follows from special relativity. I shall not take the time to explain this. I would like you to think it through. If a charge is moving uniformly, and if it radiates, then according to the principle of relativity, even a stationary charge must radiate. Now, surely that cannot be true. Therefore, only accelerated charges can radiate. A uniformly moving charge cannot radiate. And even if the charge is accelerated, it will radiate only if the second time derivative of the dipole moment exists. Now, what is the energy flux from this system of moving charges crossing a unit area dA in a unit time dt in a frequency interval d nu and going into this solid angle? That is what we defined as the specific intensity I nu. Now, the energy flux in electrodynamics is given by what is known as the pointing vector. The pointing vector is E cross H. So the pointing vector is proportional to the square of the magnetic field. I could have also written this formula in terms of the electric field, and the pointing vector will be proportional to the square of the electric field. C over 4 pi E cross H. Okay, that is the pointing vector. Therefore, we can now go ahead and calculate the specific intensity. The specific intensity, if you do the calculation, which I am not doing right now, is given by this very simple formula, 1 over 4 pi c cubed multiplied by the second time derivative whole squared. Why is it whole squared? Please remember, the energy flux is proportional to E cross H, or proportional to H squared or E squared. H and E themselves were proportional to D double dot. Therefore, the square of the magnetic field or the square of the electric field will be proportional to D double dot whole squared. Okay? D double dot whole squared. And this specific intensity will be a function of the angle. The angle is defined as the angle between the direction of propagation and some axis which I shall call as, for example, the z-axis. You can choose any axis that you like. So this is the polar angle theta. The angular distribution of this radiation in the dipole approximation will be proportional to sine squared theta and d omega. D omega is the solid angle into which it is going. Therefore, the angle, the derivative di by d omega, I is the specific intensity, which is the energy crossing the unit area per unit time per unit frequency interval and going into the solid angle, is proportional to d double dot whole squared sine squared theta. Now, if you plot this, you will find that this looks like this. This is sine squared theta. This is the z-axis. The acceleration of the particle is along the z-axis, and the direction of radiation can be anything, and the theta is the angle between the z-axis and the direction of radiation. Now, please remember that this radiation is going in all directions, and what I have drawn here is a projection. And therefore, the real radiation pattern, which is this, rotated about the z-axis, will look like a donut with a hole in the middle. So this is sine squared theta, and this is a three-dimensional representation. So the dipole pattern is symmetrical about the direction of acceleration. In other words, the specific intensity or the energy flux is zero in the direction of acceleration. That's why there is a dimple here, or a hole. There is a donut with a hole in the center. So this you must remember at all times. The radiation intensity is zero in the direction of the acceleration itself. And this radiation intensity is independent of the velocity. You notice the velocity of the particle doesn't come into it at all. What comes in is the square of the second time derivative of the dipole moment. Now let us consider a single charge which is moving and which is accelerating. What is the intensity of radiation? What does this theory give for a single charge? Now that was calculated long time ago by a physicist named Larmor, and this is known as Larmor's formula. And the Larmor's formula says that the intensity of radiation per unit time is given by 2 by 3 E squared by c cubed times the square of the acceleration. I learned this when I was in college years and years ago, but I still remember this. Intensity of radiation is 2 by 3 E squared A squared by c cubed, where A is the acceleration. Now, let us consider E squared A squared. Acceleration is x double dot. x dot is the velocity, x double dot or d2x by dt squared is the acceleration. Therefore, e squared a squared can be written as ex double dot whole squared. Ex is the dipole moment. So ex double dot is the second time derivative of the dipole moment whole squared. So that formula can also be written, this formula can also be written as 2 by 3 c cubed multiplied by the square of the second time derivative of the dipole moment. So you should remember this formula at all times, that either in terms of acceleration or in terms of the second time derivative of the dipole moment. So there are the two formula once again. Now we should ask, what will be the frequencies at which this particle will radiate? Now let the dipole moment vary with the frequency omega in a harmonic fashion. Let d be equal to d0 cos omega t or sin omega t, whatever you like. Then you have to take two derivatives. If I take one derivative, I'll get an omega. I'll take a second derivative, I'll get another omega. And therefore, the intensity of radiation per unit time will be given by 8 pi by 3 c cubed d squared omega to the power 4. All right? Now, you will say that there is something wrong because the dipole moment is d0 cos omega t. So if I differentiate it, I will get omega sin omega t. If I differentiate it once again, I will get omega squared cos omega t. So what happened to the cos omega t? Now I average it over a cycle, over a period. Then the average of cos squared theta or sin squared theta is a half. And that is where the cosine and sine have disappeared. Now please notice that the spectrum of radiation is monochromatic. There is only one frequency that I have written there, and that frequency omega. What is that frequency? That is the frequency of the oscillation. Now the charge could be oscillating either in one dimension or it could be oscillating in two dimensions, which is the same thing as going around in a circle, because two simple harmonic oscillators at 90 degrees is same as a circular motion. And there is only one frequency, and that is the frequency of radiation. The frequency of radiation in the dipole approximation is the same as the frequency of oscillation. So if a charge is oscillating with the frequency omega or going around in a circle with frequency omega, then that will be the frequency of the radiation also. So we now have the intensity, we now have the angular distribution, and we now have also the frequency content. Now let us consider the polarization from a non-relativistic charge. Remember, in the dipole approximation, you have to assume that the charges are moving with velocities which are small compared to the speed of light. So what is the polarization of this radiation? Let us say a particle is moving on a circle. Let this be the top of the table where your laptop is located. Now, if you go down and look at the plane of the orbit, if I look like this, then I will not see circular motion. I will see only the particles are going left and right, left and right, left and right. Actually, they're going round and round, but for you, it will appear like it is a simple linear motion. Therefore, the polarization will also be linear. It'll be plane polarized radiation. So if I look in the plane of the orbit, no matter from where I look, I will see linearly polarized radiation. Now let us say I look from above the table. I will see right circular polarization. If I look from below the table, I will see left circular polarization. What do we mean by right circular, left circular, linear polarization? Please remember, there is no such thing as unpolarized radiation. At any instant of time, perpendicular to the direction of propagation, if you look at the transverse plane, there is an electric field oscillating electric field, and perpendicular to that, there is an oscillating magnetic field. Now, the question is that electric field vector, what does it do over a period? It could stay fixed, in which case you say the radiation is linearly polarized, or it could go like this once every cycle. Then you will say the radiation is circularly polarized, right circular or left circular, depending upon the helicity. Or if there is no pattern at all, you will call it unpolarized radiation. That simply says that average over a period, there is no preferred direction for the orientation of the electric field. That is what unpolarized radiation means. But at every instant of time, the radiation is polarized. Now, if I look at for some different angle, I will see elliptical polarized radiation. If I look from some other direction, the circle will look like an ellipse, and therefore I'll see elliptical polarized radiation. Therefore, this is the polarization pattern from a charge, a non-relativistic charge, going around in a circle with an angular frequency omega. Now, let us go back to a collection of charges. So far we were discussing in Larmor's formula and so on, a single charge. Let's go back to our bag of charges moving with arbitrary directions and acceleration. Now, there is a fundamental theorem. A closed system of particles with the same ratio of charge to mass, E over m. So if they are all electrons, if they are all protons, E over m is the same for all the particles. It cannot radiate by dipole radiation. The charges are there, the electrons are there, they are accelerating, they are moving around madly, but they cannot radiate. Why? What is the dipole moment of this collection of charges? It is the sum over all the charges of E times R. Now, let us multiply this by m and divide by m, where m is the mass of the particle. I just like to do this. Now, if E over m is the same for all the particles, in other words, EI is the same for all i's, and if MI is the same for all i's, then this E over m is a constant. It can be taken outside the summation. And what I will have inside the summation is m times Ri summed over all I. And what is that? That is just the coordinate of the center of mass. That is how you define the center of mass, coordinate. So the right-hand side is just the radius vector of the center of mass. Now, in order to have radiation, you must have d double dot. The second time derivative of the dipole moment must be there. Therefore, it will be the second time derivative of the radius vector of the center of mass. Now, the second derivative of the radius vector of the center of mass will give you the acceleration of the center of mass. Our system of charges is not moving. The individual charges are moving. The system as a whole is not accelerating. Therefore, the second time derivative of the dipole moment is 0. Okay? The first time derivative may exist, but it is the second time derivative we need, and that is acceleration. There cannot be an acceleration of the center of mass because there are no forces acting on these charges externally. So that's an important theorem. So if I have a collection of electrons, they cannot radiate in the dipole approximation. If I have a collection of protons, they cannot radiate in the dipole approximation. But if I have a collection of electrons and protons, or electrons and ions, then there will be radiation because E over m is not the same for all the particles. And this theorem does not hold. Now, let us consider radiation from relativistic particles, because in astrophysical context, we will be dealing with relativistic particles. Now, how do we calculate the formula analogous to Larmor's formula? and the angular distribution and the polarization, etc., for particles that are moving at relativistic speed. So what you do is, let us do a trick that Fermi used to do, Enrico Fermi used to do all the time. Let us go to a frame where the charges are moving very slowly or momentarily at rest. Even if the charges are moving, if an electron is moving relativistically, I can go and jump and sit on the electron, and for me the electron is stationary. Or I can move parallel to the electron with the velocity very close to it, so for me the electron is moving rather slowly. I can always find such a frame of reference. In that frame of reference, all the formulae that I showed you are still valid because the charges are moving rather slowly compared to the speed of light. And then what you do is you jump from that frame to the arbitrarily moving frame. And then, in other words, you make a Lorentz transformation from that frame to the moving frame. And then you will get the formula. It's as simple as that. So if you do that, Larmor's formula, which was 2 by 3 E squared A squared by 3C cubed, becomes this formula. Now, what is A? A is still the acceleration. First of all, you notice that there is a second term. But more importantly, you notice that there is a gamma to the power 6. What is gamma? Gamma is a factor that comes in special relativity all the time, which we saw, is 1 over square root of 1 minus v squared by c squared. If the particle is moving at speed small compared to the speed of light, gamma is 1. But if v is comparable to c, gamma can be very large. It can be 1,000, it can be 1,000,000, it can be 10 to the power 9. All right? So you notice that there is a dramatic change when you go from non-relativistic particles to relativistic particles. In particular, there can be tremendous enhancement of the intensity. Now, why is this occurring? Now, please notice that if I take the limit when v is very, very small, gamma is equal to 1. If v is very, very small, the second term is tending to 0, I can drop it, and I will get Larmor's formula, 2 by 3 e squared over c cubed multiplied by a squared. If you really want to know how to calculate this, then you consult books like Jackson or Landau and Lifshitz, or Fermi's book on nuclear physics, where you'll find this formula derived. But it's a simple trick, and all you're doing is do a Lorentz transformation from one to another. Now, when you do a Lorentz transformation from one frame to another, many things change. Why? Because the intensity will change. As I already explained in the lecture on special relativity, the specific intensity divided by nu cubed is a Lorentz invariant. So if I go from one frame to another frame, the intensity changes. That is what we had in the Doppler boosting of intensities if the source is moving towards you. The angular pattern will also change. What are angles? Angles are y divided by x is tan theta. So if I'm making a Lorentz transformation from one frame to another, x transforms, y transforms, z transforms, t transforms, and therefore angles will also transform. And this is known as aberration. Aberration. So if rain is falling vertically on your head, if you are running very fast, it will appear to you that the raindrops are coming more or less horizontally. That is just aberration. It is not a real effect. It just appears to be so. And the polarization will also change, and the spectrum of radiation will also change. How do they change? How do all these things change? Let us look at them very briefly. The angular pattern of a non-relativistic particle accelerating in that direction is given by this dipole pattern, which can be rotated in this direction, and you got a donut with a hole in the middle, a picture that I showed you. Now, because of special relativistic aberration, this radiation pattern becomes this radiation pattern. In other words, the radiation pattern tips in the forward direction because of relativistic aberration. So you will have a hollow cone. Again, this has to be rotated. If it has to be rotated about the x-axis, so you will have a cone of radiation. Axis of the cone will be along the direction of acceleration. The cone will be hollow, and the opening angle of the cone is 1 over gamma, where gamma is the Lorentz factor, 1 over square root of 1 minus v squared by c squared. So if gamma is very large, 1 over gamma is very small, and the cone is extremely narrow. So radiation, which was going in all directions before, according to the formula sine squared theta, is now focused in the forward direction in a very narrow cone. Now suppose the acceleration is perpendicular to the velocity. Here, the velocity is in this direction, the acceleration is also in that direction. But suppose it is perpendicular, like a particle, when the particle is going around a circular orbit, the velocity is tangent to the circle, acceleration is pointing towards the center of the circle, so they are perpendicular. So the radiation pattern was like this. Once again, there is no radiation along the direction of acceleration, and this radiation pattern due to aberration becomes focused in the forward direction. Now I have a solid cone whose opening angle is once again 1 over gamma. So the important thing to appreciate is that because of special relativistic aberration, the radiation is primarily in the forward direction in a small cone whose opening angle is 1 over gamma, where gamma is the Lorentz factor, 1 over square root of 1 minus v squared by c squared. Now, because the radiation is beamed in the forward direction, the radiation will also be pulsed. Why will it be pulsed? Imagine a particle going around in a circle. It is radiating all the time in a cone which is tangent to the circle. But you will only see it when the cone is pointing towards you. So you will only see radiation from this charge which is going around in a circle from one particular location when the cone is pointing directly towards you. At other times it is radiating, but the radiation is going in some other direction. So the radiation will appear to you to be pulsed. And that's what I've indicated there. If a particle is going around like this, and if this is the cone of radiation with a certain width, and you're looking from this direction, you will begin to see the radiation when the cone is in that position, and when the cone is in that position and the particle is in that position, you will stop seeing the radiation. So you will see the radiation only for a time delta t, which is the time taken for the charge to go from there to over there. So the radiation from a relativistic particle will be pulsed as far as a single observer is concerned. Okay? Since the radiation is very strongly beamed in the forward direction, a distant observer will see a pulse of radiation. And the duration of the pulse, if you do this calculation properly, which I don't have the time to do, the duration of the pulse, which is the time taken for the charge to move from here to there in this diagram, is RC, which is the radius of this circle, divided by C, divided by gamma cube, where gamma is the Lorentz factor. So if gamma is very large, you will see the pulse for a very short duration. If gamma is slightly smaller, then you will see the pulse for slightly longer duration, but it will be pulsed. So the width of the pulse will be in time will be proportional to 1 over gamma cube. So the width of the pulse will be proportional to 1 over gamma cube. Let us define a critical frequency. The critical frequency can be defined as a reciprocal of the time delta t for which you see the pulse. And that is C gamma cube divided by RC, which is proportional to gamma cube. The important thing I want you to appreciate is that the characteristic frequency will be proportional to gamma cubed times the frequency in the non-relativistic case. If the charge was moving if the charge is moving at the speed of light, RC by C is essentially the time taken will essentially be the frequency of radiation, or omega time angular frequency of radiation. So what we are saying is that because the radiation is pulse, it will not be monochromatic either. Why will it not be monochromatic? First of all, let me repeat what I said. The radiation will be pulsed. The width of the pulse in time will be 1 over gamma, proportional to 1 over gamma cube. The frequency will be proportional to gamma cube times what the frequency would have been in the non-relativistic case. If the charge was non-relativistic, and if it is going around in a circle with the frequency omega, then the frequency in the relativistic case will be gamma cube times that omega. Now, the spectrum will be broadband, and it will be extending up to a critical frequency, and then it will cut off. Most of the energy will be at this critical frequency. I will explain this in a minute. Please bear with me for a couple of minutes. Now, here are some sources. This is the pulsar and the Crab Nebula. This is the remnant of a supernova explosion that Tycho Brahe saw in 1572. This is an X-ray image. This is a radio image. This is a radio image of a jet from a giant supermassive black hole in an active galactic nucleus. These radiation, in all these cases, are emitted by relativistic particles going around in a magnetic field. And that radiation is called synchrotron radiation. So let us discuss this in a minute. So this synchrotron radiation is very important in many astronomical contexts, such as pulsars, supernova remnants, radio galaxies, quasars, and so on. Now, here is a magnetic field perpendicular to that slide. The equation of motion of the particle, according to Newton's law, is mass times acceleration is equal to the force. And the force is Lorentz force. Charge divided by C, V cross B. So the force is perpendicular to V. It's also perpendicular to the direction of magnetic field. Now you can solve this equation. It's a very simple equation. If you decompose the velocity into two components, parallel to the magnetic field, V parallel, and perpendicular to the magnetic field, because the force is perpendicular to the magnetic field, you will find that dV parallel by dt is 0. If the charge is moving parallel to the magnetic field, it does not experience any force. Therefore, the acceleration is 0. But there is an acceleration if the velocity is perpendicular to the magnetic field. That is given by V perpendicular cross B. Now, let us say that in the non-relativistic case, when the charge is moving around with speed small compared to the speed of light, the frequency omega is known as the cyclotron frequency, because this charge, even in the non-relativistic case, will radiate. That's what we have been discussing before. And that frequency will be QB over MC or EB over MC. That is known as the cyclotron frequency. But if the charge is relativistic, then the gyration frequency will not be the cyclotron frequency, because gamma will come in the denominator with the mass, because a moving charge has a greater mass than just the rest mass energy. So the mass of the particle is m0 divided by square root of 1 minus v squared by c squared, which is what I have written as gamma times m, where m is the rest mass of the particle. So this is the gyration frequency in the relativistic case. This is the gyration frequency in the non-relativistic case. Now what we are saying is that the orbit of the particle will be, in general, not circular. In general, it will be a helix, because there could be a component of the velocity parallel to the magnetic field. But if I project this helix on the piece of paper, then it will be a circle perpendicular to the magnetic field. In general, the trajectory will be a helix. The gyration frequency, as I said in the previous slide, is EB over gamma MC. Now, let us see, the total power radiated. The total power radiated by a charge with a gamma, with a Lorentz factor gamma, but gamma is 1 over square root of 1 minus v squared by c squared, then the energy radiated per unit time is given by this formula. And the important thing is to notice that it is gamma squared times b squared. All right? So, the energy radiated per unit time by a relativistic particle going around in a magnetic field is proportional to gamma squared. It is proportional to the square of the magnetic field, and it is inversely proportional to the square of the mass of the particle. Therefore, if an electron is going around in a magnetic field, and if a proton is going around the same magnetic field, even if they have the same energy, the radiation from the proton will be 1,000,000 times less, because this intensity of radiation is proportional to 1 over m squared, and the proton is 2,000 times more massive than the electron, and the square of that will give you a factor of 1,000,000 in the denominator. So, you should always remember that if a charge is relativistic, then the intensity of radiation is proportional to gamma squared. And if it is going around in a magnetic field, it's gamma squared times b squared. And in all cases, there will be 1 over m squared in the denominator. Now let us look at the spectrum of radiation. Let us say the charge is moving non-relativistically in a circle. Then if you are looking at it, if the charge is moving in this plane, and if you are looking at it from there, then you will see the electric field changing sinusoidally with time, sine omega t. Now if I Fourier transform sine omega t, then I get a single frequency, or in other words, the power spectrum. As the electrical engineer would call it, the power spectrum consists of a single frequency. That frequency is omega. Now suppose the electric field is changing not quite sinusoidally, but if that sine wave is slightly distorted, then the power spectrum will have harmonics in it. It will not have just the fundamental, but it will have harmonics. I hope you have learned something about Fourier series and Fourier transforms. So if you have Fourier transform of a sinusoidal wave, is a single frequency, but if it is not quite sinusoidal, then it will have harmonics in it. Now suppose the electric field changes with time like this. And why would it change like this? Because I'm now looking at an electron which is relativistic going around in a circular orbit. And because the intensity is beamed in the forward direction, the intensity of the square root of that will be the electric field. Remember, the intensity is proportional to E squared, H squared. Pointing flux is E cross H, which is proportional to E squared or H squared. Therefore, the electric field will be highly intense compared to the non-relativistic case. So instead of being a simple sine wave, I will have pulses. The electric field will be in pulses. And if I Fourier transform that, you will find all kinds of harmonics. You will find not only the fundamental, but you will find all kinds of harmonics. In other words, the spectrum of radiation from a relativistic particle, because the radiation is beamed in a particular direction, the spectrum will consist of all harmonics of the gyration frequency. The gyration frequency, omega b, is EB divided by gamma MC. All harmonics of it will be present, and therefore the spectrum will be broadband and will peak at a certain frequency. Now, if there is a distribution of electrons with different energies, since the gyration frequency is proportional to 1 over gamma, because the gyration frequency is EB divided by gamma MC, the harmonics of various charges will be at different frequencies. Please remember, the characteristic frequency of radiation from a given charge will be gamma cubed times the gyration frequency. The gyration frequency will be different for different charges because gamma of different charges is different. Therefore, you really will have a continuum of radiation. That's all I'm saying. So if you take the Crab Nebula, there is a collection of relativistic particles with different accelerations and different gammas. They will all radiate at different characteristic frequencies and their harmonics, and therefore the sum total will be a quasi-continuous spectrum. Please remember that the spectrum of synchrotron radiation from a single electron is very sharply peaked. This is the log plot. Log of intensity was log of frequency. So this is an extremely sharply peaked curve, peaking at the characteristic frequency, which is gamma cubed times the gyration frequency. Now, synchrotron radiation spectrum, in the non-relativistic case, which is the cyclotron radiation, most of the power is radiated at the cyclotron frequency, which is EB over MC, which is the period of oscillation. But in the relativistic case, the spectrum is not monochromatic. It extends up to a critical frequency, which is gamma cubed times the gyration frequency. And the gyration frequency is EB divided by gamma MC. Therefore, the maximum frequency up to which the electrons will radiate will be proportional to B times gamma squared. Why? Because omega B is EB over gamma MC, so that is the B that comes here, and gamma cubed divided by gamma becomes gamma squared. So, if the strength of the magnetic field is 1 Gauss, and the charge is non-relativistic, then the frequency of the cyclotron radiation will be 3 megahertz. 3 megahertz, because gamma is 1 and B is 1. Now, if gamma is 1,000, then the frequency at which it will radiate will not be 3 gigahertz, but it will be 3 gigahertz multiplied by 1,000,000. So it will be 3 times 10 to the power 12 hertz. So the frequency will not be at radio wavelength, but the frequency will be in gamma rays. In a real situation, there will be a distribution of charges. They take in the Crab Nebula, the number of particles with energy E as a function of E will be some power law, e to the power minus p. That's because that's the distribution of charges supplied by the central pulsars, as we shall discuss in a couple of lectures. Then each particle will radiate a spectrum like that, which is sharply peaked. This is the log plot. It's sharply peaked. And the peak will occur at different frequencies for different charges because their gammas are different. So I'll be stacking up sharp curves like this. And if I put them all together, I will get that red line over there. So if I have a collection of charges, then the intensity of synchrotron radiation as a function of frequency will also be a power law. That's all I'm trying to say. We have a single charge. The matter is simple. There will be a sharp peak at the characteristic frequency. But if there is a collection of charges with different gammas, you will have a sloping curve over there. Now, we have gone on for a long time, and it is rather important, and please permit me to go on for a few more minutes to wind up our discussion. Now, synchrotron, this is a picture of a supernova remnant in the constellation Cassiopeia A. This is a radio image, and what you see here is synchrotron radiation from a power law distribution of electrons. Now, before I wind up this lecture, let us first quickly review what I have said about radiation from accelerated charges. Charges will radiate only if it is accelerated. If the charge to mass ratio of all the particles is the same, then there will be no radiation in the dipole approximation because there is no acceleration of the center of mass coordinate. The total intensity of radiation from a single accelerated charge will be given by Larmor's formula, 2 by 3 E squared A squared by C cubed. And because E squared A squared can be written as the square of the second time derivative of the dipole moment, the intensity of radiation from a single charge can also be written in terms of the square of the second time derivative of the dipole moment. If the charge is non-relativistic, the radiation will be monochromatic at the gyration frequency. And the radiation pattern will be dipolar, and there will be no acceleration in the direction of acceleration, which is always directed towards the center of the circle. But if the charge was relativistic, then the radiation will be highly beamed in the forward direction because of special relativistic aberration, and the width of this cone will be proportional to 1 over gamma, and since the Lorentz factor gamma is very large for a relativistic particle, the cone will be extremely narrow. And because the radiation is beamed in the forward direction, the radiation will be pulsed. And because it is pulsed, it will not be monochromatic. It will be a quasi-continuous spectrum, and it will peak near the characteristic frequency, which is gamma cubed times the gyration frequency. What about the polarization? The polarization from a non-relativistic particle, if you're looking in the plane of the orbit, it will be linearly polarized. If you look from above or below, it will be right circular or left circular. In a general direction, it will be elliptically circular. In principle, there is radiation in all directions except in the direction of acceleration. But in the case of relativistic charge, the radiation is confined essentially to the plane of the orbit. Therefore, the radiation will be 100% linearly polarized. If I look, if there is a charge going around in this plane, in this piece of paper, relativistic speed, if I look from above, I don't see any radiation. If I look from below, I don't see radiation. I see radiation only if I look in the plane of the orbit, and there the radiation will be 100% linearly polarized. And the plane of polarization will be in the plane of the orbit. The total power radiated will be proportional to gamma squared, it will be proportional to b squared, and inversely proportional to the square of the mass of the particle. Now, if you'll permit me a few moments, I would like to tell you about a different kind of radiation, which is known as Bremsstrahlung. It's a German word which means break radiation. Strahlung is radiation, break radiation. When I decelerate or accelerate, it doesn't matter, because acceleration comes as square. So it doesn't matter whether I'm decelerating or accelerating the particle. So if I have an electron which comes near an atomic nucleus, it will be deflected. And because it is deflected, its velocity is changing. And therefore, it's experiencing an acceleration. And therefore, it will radiate according to Larmor's formula, 2 by 3 E squared A squared divided by C cubed. This is Bremsstrahlung. When an electron bombard a metal plate, for example, they are decelerated, their motion is braked, and they will radiate. This is known as Bremsstrahlung, or English translation is brake radiation. In an electron-electron collision, there is no radiation in the dipole approximation, as I said, because E over m is the same. In a proton-proton collision, there is no radiation in the dipole approximation because E over m is the same. So if the charge-to-mass ratio is the same, there is no radiation. But if I have a collection of electrons and ions, there will be radiation. So when an electron collides with an ion, it will radiate, and that will be the intensity of radiation. Now, if you have a problem with your foot after playing football, you go to an orthopedic doctor and takes an X-ray. How are these X-rays produced? This is how it is produced. An electron gun fires electron with high velocity into a metal plate, and the electron decelerates and comes to a stop after a certain distance. And this decelerating electron emits radiation. Now, in an astronomical context, what you're looking at is the sun at various frequencies, ranging from 80 megahertz to 17 gigahertz. This radiation is produced because the sun, everything is ionized. Of course, interior of the sun is opaque, but in the outer regions of the sun, the electrons collide with ions, producing Bremsstrahlung radiation, and that is the origin of this radio radiation that you see. If you look at the sun with an X-ray telescope, say, for example, the Chandra X-ray telescope, you see the sun is bright in X-rays. Once again, this is due to Bremsstrahlung, very high energy electrons scattering off the ions. Now, if you look at this supernova remnant, Cassiopeia A, this is now an X-ray image taken with the Chandra telescope. This is again Bremsstrahlung. The expanding debris of a supernova explosion is very hot. Its temperature is about 10 million degrees. So if high energy electrons collide with ions, it produces radiation, this time peaking in X-rays. So that's a very brief summary of Bremsstrahlung, which is extremely important in astronomical context. We will encounter this again and again and again. And I did not have the time to go into the theory of this, but perhaps you can read about it, and perhaps as and when I refer to Bremsstrahlung, I will hint at some of these formula. So with that, I conclude this ultra-rapid review of radiation from accelerated charges. I do plead with you to go and listen to this video a couple of times, because in your courses in electrodynamics, you would not have learned much about radiation theory. And in astronomy, it is only radiation that matters. Okay? So in the next lecture, now that we are prepared with basic ideas of special relativity and general relativity, and about radiation from accelerated charges, we are now ready to discuss more exotic objects. In the next lecture, I shall discuss white dwarfs and Chandrasekhar's famous theory of white dwarfs. I shall argue that white dwarfs are actually quantum stars. Thank you very much for listening.